The company is called Independent Neuroscience Services, and we're based in the United Kingdom in the countryside between London and Brighton, as you can see here on the screen. But at the moment, I'm actually talking to you from a different place, from what I'd like to call my winter hibernacle office in the very south of Germany, right at the border to Austria. So the border between Germany and Austria is actually just at the end of our garden. It's about 30 meters behind me. And if any of you have seen that 1960s movie called The Sound of Music, there was filmed 20 minutes up the road from here. You know that this is kind of what the landscape looks like, right? And this is what the people look like, and we all sort of dance around the meadows and sing about how the hills are alive with music. And one thing about when you're surrounded by mountains, and you'll find yourself driving through a lot of tunnels, right? And today I want to start my talk with a little animation of the type of machine that is used to bore tunnels through mountains. It's called a tunnel boring machine, a TBM. And I mean, these are really cool machines. But the reason why I'm showing you is not just that it's a cool machine. I also think it's quite a nice metaphor for the whole sort of scientific endeavor at large, right? So the orange bit there at the front, that's the cutting edge, right? And this metaphor, this basically represents all of you guys, right? The scientists that are sort of breaking new ground and push hard against the rock until you eventually make a breakthrough, right? And so breakthrough, right? This is what it looks like in a tunnel boring machine. And you know, you hear all the excitement. That's like the best part of the job, both in tunnel boring as well as in science. After you grind away for years, and then there's, all the politicians come and take pictures here, right? Everyone applauds, and there's parties and music and speeches and so on. That's all wonderful, right? But of course, at that point, the tunnel isn't actually quite finished yet, because in a tunnel boring machine, there's not just the cutting wheel at the front, but there's also all this sort of trailing support machinery there at the back. And that serves basically two main tasks. So one is to support the drill face. It has this sort of corkscrew mechanism there that moves all the broken down soil away from the drill area. And then there's these huge hydraulic cylinders that push the drill face forward into the rock. And there's control rooms there in the back and transport mechanisms and all sorts of things to make the drilling possible. But then it also serves the function of building the tunnel behind that drill face. So it installs these concrete lining segments behind the drill area to stabilize the ground, and that forms the actual tunnel. And when we later drive through that tunnel, we don't even think about how much work went into building that tunnel in the first place. And the analogy that I'm trying to illustrate here is that in a scientific endeavor, you have all the people at the cutting edge, the professors and postdocs and PhD students who make the breakthroughs. So that's all of you guys there, this orange bit at the front. But then there's all this trailing machinery there that represents the lab managers and the scientists in the core facilities and the animal house staff and the janitors and the mechanical workshop guys and everyone else. And that also includes external companies that provide tools and reagents and equipment and all of that. So, and they also all have this twofold role, where on the one hand, this support machinery is there to support you on the way to the scientific breakthrough. But they also, in a sense, line the walls behind you, right, with concrete segments, and they build up solid structure so that this progress that you're making at the front can then serve for others to follow in your footsteps without even noticing how hard it once was to break through that rock in the first place, right? So I'm not really sure whether this analogy makes much sense to anyone other than me, but that's how I see myself. That's how I consider my job, as being part of this sort of support machinery, where I'm helping to disseminate technology and support people that need this sort of assistance with 2-photon microscopes that to do their job at the cutting edge. And traditionally, if you have a project that requires a 2-photon microscope, there's really, you have two options, right? You can buy a commercial turnkey system, or you can build your own DIY system.
Bruno,
yes?
Just real quick before you move on from the analogy, where do for-profit publishers fit into that?
Say it again?
Where do for-profit publishers fit into that analogy of the tunnel boring machine?
I think that depends a lot who you ask.
Okay.
But we can discuss about that later. I have a few ideas how they fit into that model.
Okay.
Yeah, so the two options that you normally have, these sort of commercial turnkey systems, or building your own DIY system, and each of those has their advantages and disadvantages. I've listed some of them here. Where in the turnkey system, you have a pretty steep price tag, and they are built with a closed design, meaning that you can't really adapt them to your specific requirements. But unless you talk to the vendor and they make those changes for you, I mean that's sometimes possible. But the plus side is that you don't need much prior experience. You can go in and use it, and if you believe the commercial vendors, then it's as simple as opening a fridge. And but they build everything for you and they train you how to use it and so on. On the other end of the spectrum, you have these open source DIY systems that have a much lower price tag, and the design is completely open. There's numerous publications out there that tell you exactly how to build them and provide all the details, and that's great because you can easily make changes and add new components when the requirements change and so on. Also, if you want to build something that has just recently been published, isn't commercially available yet, then self-building is really the only option that you have. The downside is that it does require some prior expertise, and it can become quite a time sink for a PhD student or postdoc who is building that system. Now, if you're really lucky and you have access to an excellent in-house neurotechnology core facility, like the guys at Janelia or at Harvard, in some other places, then and then you can just tell the core facility scientists what you need, and they'll build it for you, right? And that's wonderful. But not every neuroscientist has this luxury, and they are at the moment just left with those two options, or at least until a few years ago. And then and I thought, well, there's got to be a way to help those people with self-building. And I've built a few microscopes in my time where I can start offering that service and see if people like it. So I call it an INSS-assisted DIY system. So this falls somewhere between those two categories. It's a little bit more expensive than completely self-built system, but it's still much cheaper than a commercial turnkey system. And then a lot of things are the same as with a fully DIY system, where the design is open and easily adaptable. There's no vendor lock-in. You can make any changes that you want, right? The advantage is that you don't have to do it all by yourself, right? I can help you to figure out what the options are and how they fit the experimental requirements, how they fit the budget. We generate CAD drawings for your microscope, and we assist with purchasing all the components, and then we come to the lab and build it with you. So you don't really need much prior expertise for this. We can teach you a lot while we're building it, but it would, of course, still be good to build this with a person who has a bit of a technical mindset, because at the end of the day, it's still a DIY system. It doesn't come with training wheels in the same way as the commercial turnkey systems. And it does require a little bit more technical engagement from the end user than the fully commercial turnkey systems. Now, what would an assisted DIY microscope look like? I've put some examples here, right? So here in the center, it's a 2-photon microscope for in vivo calcium imaging. There's lots of space under the objective here for any sort of behavioral apparatus, and there's a dual color epifluorescence camera imaging on the system on top. It has another LED here for 1-photon optogenetic full field stimulation. And so this was, purpose built for those requirements that this client was asking for. And here at the top corner, you can see one where the client already had this virtual reality system, and they asked us, like, could you build a 2-photon that fits exactly over it? Like, she had researched other options, and there wasn't really anything that that she could fit, like they're from the top in the same way that we could build it there. And some spaces that we're working in, like, you know, this is for example, this is in central London. There's not that much space in the room, but they needed this large laser. The laser takes up basically 2/3 of that table. So we then, you know, built the microscope over that laser to still give space here at the front for behavioral apparatus and so on, right? And a similar scenario was here in this video on the bottom right, where we built like a multi-story microscope, again, because there wasn't much space. So there's a laser at the bottom. You can see that there's this coherent laser. And then in the middle layer is a custom pre-chirper that we built together with APE Berlin. And then on the top is this movable scan head. Then I guess the next thing I want to talk about is how we build these. And it's actually relatively easy, right? So here's a quote that I found. I wonder if anyone recognizes where this is from. So this says, building a 2-photon microscope is easy because most of the work is done by the laser itself. All the microscope needs to do is to focus the laser light to a point, move it across the preparation, and measure the fluorescence photons emitted. These jobs are done by an objective, a scan engine, and a detector, respectively. That's all there is to it. So this is actually the opening of a book chapter that Spencer wrote in this neuromethods book. And I mean, this is what he's saying there is very true, right? All you need is a laser, an objective, a scan engine, and a detector, and that's all there is to it. It's not magic, right? So I'm actually going to spend the rest of the talk just discussing how trivial it really is. So let me take you back a second to your days in secondary school and just revisit some of these extremely simple concepts, right? If a ray of light encounters a boundary between one medium and another, then one thing that happens there is reflection. And of course, the angle of incidence is equal to the angle of reflection. And we use this law of reflection when we steer the beam with a scan mirror. So if you rotate the scan mirror, or if you were to rotate this slab here back and forth, right, then the angle between the incident beam and the reflected beam would actually change by twice as much, because the angle of incidence changes by a certain amount, the angle of reflection changes by the same amount. So then, so when you see a spec sheet of a scan mirror and says the scan angle is plus minus 15 degrees, that usually means those optical degrees, and that's 2 times the mechanical rotation angle, right? So that's the first thing that Spencer said we need, right? We need to move it across the preparation. So that's what we do. We use the scan mirrors, usually 2 mirrors, a fast mirror in one dimension, a slow mirror in the other, to create a raster scan pattern. Now, of course, the other thing that happens at the interface is called refraction. So the ray changes direction as it enters a new material, and the new direction depends on the angle of incidence and the refractive indices of the 2 media. So the refractive index is just a number that indicates how fast light travels in a given medium. So n equals the speed of light divided by the phase velocity in the medium. And the law of refraction says that n1 times sine theta 1 equals n2 sine theta 2, or in other words, the more the light slows down at this interface, the more it bends towards the normal. And then as it speeds up again, as it exits the material again, it just bends away from the normal and then comes out, of course, parallel to the incident beam. Now, I've got to deviate again a little bit about this topic of Snell's law. That's named after Willebrod Snell. And that's kind of funny, because Snell was neither the first to discover this law of science, nor was he the first to publish it. So he figured it out around 1621, but the English mathematician Thomas Harriot had already discovered it probably around 25 years earlier than that. But for some reason, neither of the two, neither Harriot nor Snell, actually published this, and then they both passed away in the 1620s. Right? And it wasn't published until René Descartes published it in 1637. But then somehow Snell still got the credit for it because Huygens attributed it to him about 70 years later than that. But the cool thing about this is that it should actually really be called Ibn Zal's law, because there's a Persian mathematician called Ibn Zal, and he discovered the law of science more than 600 years earlier than any of these other guys. And he did actually publish it. So he published this book of burners in AD 984, so over 1,000 years ago now. You can see this this illustration here of a spherical lens, but this diagram here at the top, that illustrates the law of science. So if you have an incident beam here, right, and that beam is refracted here, and then you extend this refracted beam here with this dashed line, and you draw a right angle here, then what he's showing in that diagram is that if you divide the distance BD by the distance AB, then that's the ratio of your refractive indices, and that's sine θ1 divided by sine θ2. So it's kind of really cool that this was known over 1,000 years ago, but then somehow forgotten and then rediscovered in the 17th century. And it wasn't actually until the 1990s that people realized that that Ibn Zal was so far ahead of his time there. But what this means is that, you know, if you know the angle of the incident ray and you know the refractive indices of the materials, then you know where the ray is going to go. So if you do this on a curved surface like a lens, you just need to know the curvature to work out the angle of incidence between the ray and the normal. And you need to know the refractive index of the material. And then you can work out exactly how each ray of light bends as it enters the lens, as it exits the lens, and then you know where it comes to a focus.
Sorry to interrupt, Bruno. I have just a quick question, which is, do you know if it was a glass type material, or was he using water droplets or oil droplets? So, you know, like, so.
No, I think it was a glass type material. It was some sort of crystal. I'm not sure exactly what material it was.
Okay, cool. Yeah, thank you.
But it wasn't a liquid. It wasn't a liquid.
All right, thank you.
Yeah, so you know where the light here is coming to a focus, and just another historical note there. Focus is actually the Latin word for fireplace, because, you know, in the old days lenses were mainly used to set stuff on fire, so hence the name focus. So so now we know how to focus the laser light to a point, and of course there's a caveat here, because the geometric optics that I've showed here, it is a somewhat simplistic way to look at this, and if you really want to understand what light actually does, then Fourier optics is a much better way to do that, and I think Nico will tell you all about Fourier optics later today. But for the purpose of building a two-photon microscope and you know, knowing where the beam goes, the geometric optics is actually sufficient. You just need to know the refractive index of the material and the curvature, and you're good to go. And of course, those parameters, you can, you know, the lens manufacturers will tell you that, right? Here's a screenshot from the Thor Labs website, and on the left-hand side here, this is just a list of some very basic uncoated biconvex lenses. Of course, in real life, we would use much more sophisticated lenses, but you know, to explain the workflow and to understand how straightforward it actually is to think through a beam path like that, the biconvex lens will do just fine. So you know, you find the radius of curvature. It's listed here, right? It's got the same radius of curvature on both sides, and it's got a thickness to it, and N-BK7 here that indicates the material. So you can then go to refractiveindex.info and look up what the refractive index is, right? And then with this info at hand, you can, you know, sit down with a piece of paper and work out by hand exactly where the rays are going. Before the invention of the digital computer, lens designs were actually hand calculated by humans, and they had the job title computer, and there were usually, you know, hundreds of them in a large sort of open plan office, each calculating a little bit of the lens design. But of course, nowadays you use software to do that, and a popular software tool for this is called Zemax. So you can take the info from that lens here and then Zemax is basically it's kind of a glorified spreadsheet program, right? So you've got these rows of parameters here, and really the important ones that we're looking at here is for this lens a radius. It's got a thickness, it's got a material, and then on the other side, it's got a negative radius because it's curved in the other direction. And Zemax then tells you exactly where the rays are going. So if you send collimated light in, it will come to a focus. And then if you pick another biconvex lens from that list, again you enter here the parameters for this lens, the radius and the thickness, the material, and so on. And obviously, you don't actually have to enter this by hand. Zemax has lens catalogs where you can just pick from those, pick a lens, and then it automatically populates the spreadsheet. But it then calculates exactly how far apart the two lenses you need to put them in order to get collimated beam out the other side, and it's of course going to be the sum of the focal length of those two lenses, or at least close to this, right? So now you have a simple beam expander, right, or a Keplerian telescope, and then when you add a scan mirror to that, like that. So here now the colors now represent different angles. Then what you have is basically a scan engine. You can then use Zemax to analyze the performance of the scan engine and see what sort of aberrations you get for different wavelengths and for different scan angles and so on. But if you're satisfied, obviously with these biconvex lenses, you probably wouldn't be satisfied. Although you could get a laser scanning image with this, but it just wouldn't be as great as you would want it. So you optimize and try different lenses until you're satisfied, and then Zemax tells you exactly where to position those lenses, and you can then export this file as a so-called step file for using computer-aided design software such as SolidWorks or Autodesk. So that's going to be that's usually then the next step in our workflow, where you import that, you see this, you see the same lenses and that same sort of scan engine, and then you go and put some lens tubes around them, right? And you can add some posts here, right? You add an objective, and it's really quite easy to learn this software, right? I mean, this might take you a few hours to get into the into this workflow, but and these step files for all these other components, they're available from the manufacturer's website, so you can just try a gazillion different tubes and mounts and posts just to fit around the desired lens positions, to make something that works from the mechanical perspective around that. So now we have an objective in place, we have a scan engine in place. Now the last thing we need, according to Spencer's guidance here, is a detector. That's typically a photomultiplier tube, and we also need to bring the light from the back aperture of the objective towards the detector. So we again use the same workflow, starting with Zemax, and so this is now a more realistic example where the back aperture will be located here, and the light that emits from all positions of the back aperture will then get reflected here with a dichroic mirror that separates the excitation laser light from the emitted fluorescence. Then is collected by a 2-inch collection lens, and then we've got a few other sort of apertures here that we need to consider. We've got a fold mirror here that's just 100% mirror, a few more filters, a few more lenses, and then here at the position of the photomultiplier detector, ideally you have the entire back aperture of the objective demagnified to the size of the photocathode of your PMT detector. And once you're happy that you get enough of you capture enough of the light that's coming out of the back aperture, you then go and put some Thorlabs components around it, and some Hamamatsu components. So these are the PMTs here. In this scenario, there's actually another port here for another PMT that we left unpopulated in this case. So and once we know what sort of components we want for this, then we just put the metalwork around it, and then this is what it looks like in the end when it's up and running in the lab. So I'm going to show you a few other examples of some of the things that we've built. So this is a remote Z-scanning paper here by Peter Rupprecht. And a client of ours came and said, look, it's this paper from Peter Rupprecht about remote focusing. Can you help me build this? Right? This is the same principle that Caspar already explained yesterday, where you have a small mirror here that moves up and down, and it's conjugated to the specimen plane. And when the mirror moves up and down, the focal plane and the specimen moves up and down, and it does that without having any sort of physical movement near the sample, which is sometimes a bit of a downside when you physically move the objective. So we looked at the paper, and then we went through our sort of usual workflow. Our scan head is a little bit different to the one that was in the paper, so it looks a little bit different here, but this is the position of the mirror. We've got a lens here, quarter wave plate here, conjugated to the specimen plane, and put some Thorlabs components around it and so on in the CAD software first, and then go to the lab and build it. So you can see here that we've got the light coming up through the periscope here. There's a polarizing beam splitting cube here that directs the light into this side arm, goes through a lens. There's another lens here, quarter wave plate here, another lens. This is the fast mirror that moves back and forth with this voice coil actuator here. And then it goes back, and on the way back goes through the quarter wave plate again, and then straight through that polarizing beam splitting cube into the scan head. Right? Another project that we've done recently is from this paper. There's a similar situation. Client comes and says, "Oh, there's this nice optogenetics paper. Can you help me build something like that?" And this is a very cool holography technique called 3D shot that Nico developed when he was a postdoc with Hilda Desnick and Laura Waller. It's the same story, right? We read through the methods section and say, well, yeah, that looks doable. We figure out what all these lenses do, why they do it, how they do it, and so on. Like, we don't invent any of this, right? But we try to help clients replicate, follow in the footsteps of someone who's made this progress already, and follow them for their experiments. So then we model that again in Zemax, and then as before, we put some metalwork around it. And now, unfortunately, I can't actually show you a real life picture of this one because we haven't built it yet. Caspar mentioned yesterday about about the supply chain chaos. We are obviously affected by that as well. So this project's been delayed by a few weeks. So hopefully in April or so we can get this working. Now,
Bruno?
Yes.
Sorry to interrupt. I'm curious where you got your voice coil. You showed a pretty beefy voice coil actuator for the remote focus.
That's commercially available from PI Physikinstrumente.
I didn't know they made voice coils. Okay, thanks.
Yeah, they do. So the last project I want to talk about briefly is the Diesel 2P that was developed in Spencer's lab and then published last year. That's a mesoscale 2-photon microscope with 2 independent scan engines. And that allows you to image 2 independent regions with a 5mm field of view by means of temporal multiplexing. So that's kind of similar to what Grace talked about yesterday, but her laser has a repetition rate of 31.25 megahertz. And she then subdivides this into 4 interleaf beams. And this laser here is an 80 megahertz repetition rate, and it's split into 2 beams. So 80 megahertz, the pulse interval is 12.5 nanoseconds. So you need to delay one beam by 6.25 nanoseconds. And as a rule of thumb, an easy thing to remember is that 1 nanosecond is a light foot. So that means the speed of light is approximately equal to 1 foot per nanosecond. And a foot is roughly 30 centimeters. So in 6.25 nanoseconds, light travels approximately 1.87 meters. So therefore, if one of the two paths is 1.87 meters longer than the other, then your two pulses arrive at the sample interleaved from each other. And then from the arrival times of your emitted photons, you can basically reconstruct which of the two paths has excited the fluorophore at that instant of time. Now, in this project, we didn't actually do any of the ZMAX modeling. Spencer's team made that design available in their paper. And then our client purchased that entire optical assembly for scan engine and objective from a commercial supplier. So we just helped them to figure out how to place it on the table, and how to configure the beam path on the table and build a delay line and all of that. And then get it up and running and get it to work. So this is you can see here, this is just for scale, my hand next to the objective. It's quite a large objective, very nice design. And then when you scan a beam on this viewing card here, you can see that you've got these two independent scan engines, and you see that the circle on this target, the outer circle is 7 millimeters, the inner circle is 1.6 millimeters. So you have a really nice large field of view. So when you use this with a Gcamp mouse, you can take an overview of your entire sort of cranial window there and place these two different these two stripes there anywhere in this field of view. And then when you zoom in, you can see how nicely you can record these cells there anywhere in this large field of view. So this is really exciting work that Spencer's lab has done there, and I feel very privileged that I get to play around with these things occasionally too, when I help other people to follow in his footsteps there. So yeah, I guess in summary, building a two-photon microscope is easy. It's really just a bit of Eben-Sauer's law plus a femtosecond laser. And everyone who's in this workshop could easily do this themselves, right? But of course, it does take a bit of time to put these drawings together and make a list of all these parts, and then email all the different companies for pricing and place all the orders for all the parts, and then chase the companies, and when your deliveries are delayed, and like all of that stuff takes time, right? And at the end of the day, right, if your scientific interest is primarily in figuring out how the brain works, then it's a massive opportunity cost to spend too much time on those sort of menial tasks, like running back and forth in the bowels of this boring machine, right? I mean, of course, if it's part of your scientific interest to advance the field of microscopy itself, and you're creating these badass microscopes like Casper and Spencer and Grace and Nico and Darcy and Emily and all the other workshop speakers, right? I mean, that's a different story. Then that's your research. That's the cutting edge, right? But if you're primarily a neurobiologist, and microscopes are more of a tool than a research focus in your work, then you might be just better off if you do it as an assisted DIY project instead of building it yourself. Right? So that's basically all from me at the moment. I just want to quickly thank my team. I have a few people working with me: Simon, Angelos, Lionel, Mark, and Eleanor, who are all amazing. And yeah, if anyone has any questions, if we have time, you can ask them now. Otherwise, you can obviously email me at this email address there. Or yeah, that's it from me. Thank you very much.